So I'll be talking about our journey towards safe, reliable, and trustworthy AI. These are topics that I'm personally very interested in. But as Adrian mentioned, more recently I've been spending a lot of time on science, and I will cover a bit of that work as part of the talk as well. So I'll start by sort of saying that, well, we all know that AI and machine learning is a very powerful technology, and it can help us sort of tackle some of the key challenging problems that the world is looking at. I mean, just to give you three sort of examples that are even in the organization that I work in, sort of improving sort of wind power, sort of reducing the energy sort of consumption of data centers, and more recently AlphaFold. Now, all these are extremely important, impactful problems, and we have shown how machine learning and AI can sort of make a difference in these problems. The question is, how do you know that you have actually sort of solved a problem? How do you check that the problem has been solved? To give you an example of how this is not trivial in the case of machine learning, we all know about image classification on ImageNet. And so ImageNet is this incredible sort of resource over a decade long. All of us sort of know it and appreciate what it has done to accelerate progress in deep learning. And you will see these images in ImageNet, and these are sort of images of birds and cats and dogs, and different species of in fact, dogs and cats and birds. And some of the best sort of classifiers are able to get all of these images correct. And in some sense, they are superhuman in their ability, because I, for one, am not really good at this particular task of detecting the exact species there. The same superhuman perception networks do this, right? They will take they suffer from these adversarial examples. They label the image on the left as a school bus, but on the right as an ostrich. And so what is happening? What has happened is basically they don't conform to this implicit property that we were assuming, that if you make an imperceptible change to the input, the answer should not change, or the prediction of the network should not change. And somehow the model failed to conform with this property or this specification. And there was nothing in the whole learning paradigm in our empirical loss estimate. Of course, we have a regularizer and so on, but somehow the regularizer or the biases were not enough to prevent this particular phenomena from occurring. And this is not just an issue, like generally it goes and talks about a broader issue, that when you think about a problem, a definition like image classification, you can't assume that by just having performance on a specific data set like ImageNet or MNIST, that if you have high accuracy on ImageNet or MNIST, the problem is solved, right? So this implication that if you have high accuracy on a particular data set, that means the problem has solved, is really not true. And it's not just a problem that we see in image classification, that image classification somehow sort of has this unique characteristic. It's something that you see all over, and all the problems that you sort of consider. So of course, we have seen this in the context of image classification, where we have flying pigs, if you add some sort of noise. But it's also true if in the context of language, where a small typo might completely change the prediction from a positive sentiment to a sort of negative sentiment. NLP systems also suffer from these kinds of effects. And not just NLP systems, audio systems also suffer from this effect, right? So you take a speech transcription system, it works really well for the sample, and now you sort of add some imperceptible noise, like a human might not even basically notice, and the system's transcription completely changes. And it's not just even prediction tasks. Even representation learning at a very basic sort of level, when you think about representations or what representations are being learned, if you take a sort of normal variational autoencoder and you add some sort of noise to your input and then sort of produce the encoding and then try to decode it, you might get a completely different result. So here, by just adding this little bit of noise to XA to obtain this image XP, this noisy image XP, a human might say, okay, well, the performance might change. But X dash, the thing that has been reconstructed, is completely different, right? So at a fundamental level, the representations that are learned sometimes can suffer from these really, really problematic situations. So and in this particular case, what happened is the representation, the encoder, did not sort of satisfy the condition that it should not be overly sensitive to meaningless changes in the input. And in this case, the meaningless sort of change was this addition of noise. And it's not just these kinds of specification of being oversensitive to certain types of perturbations. There are other kinds of issues that also are extremely important, particularly around distribution shift that we see in many different applications. And there are different kinds. You can have spurious sort of correlations. Camels often occur in deserts, but then if your system sort of tries associating that camels and deserts are the same thing, then that is a problem. Then there is property shift, where the data is not collected across different ethnicities and gender, and we have we have seen the effects of that. And finally, label and property shift. You want to sort of build a system which can diagnose tumors in all hospitals, in all settings. You don't want it to just be trained for a particular sort of scanning machine or scanning sort of operating sort of parameters. And so why is this a problem? You get unfair sort of outcomes among groups, as has been shown by this studies called gender shades. You get sort of non-robust, non-reliable outputs in the case of deployments of machine learning, in the case of diabetic retinopathy. And then in the context of language, you see really problematic results coming out of language models. So fundamentally, what is happening is that our learning process is essentially a transformation of changing an incomplete specification, which is in the form of training data. And this training data is biased and it's limited. And learning is transforming that into a model. And of course, there are certain things that we have put in, like having a good inductive bias, having good regularizers, and so on, but that's not enough. And because at the end of the day, you're just evaluating and assessing the performance of the model on some test data, and that evaluation protocol is not foolproof. So here we sort of bring in the notion of coming from software security. And when you think about software development, you think about properly verifying or formally sort of checking what kinds of properties any software system or any program needs to be consistent with. And this is where what I would sort of say, this notion of specification guided machine learning, where you are not just saying that the learning system has to learn from experience, but also has to be consistent with certain properties or certain specifications that the designer had in mind when they were sort of thinking of building the model. So this notion of spec consistent AI, what kind of specifications sort of you want specifications around safety, where you want to satisfy critical safety properties, which should always be true. You want the system to be reliable in the sense that it should generalize to real world variations. It should know when it doesn't know. It needs to have calibrated uncertainty. You could have specifications of that type. And then it should be trustworthy in the sense that it should be explainable, fair, private. And there are sort of ways to formally specify, like what does it mean to be explainable, fair, or private. And of course, this is sort of a research topic in itself. Now, when you think about spec consistent AI, how would you implement it? So the first thing is you first have to formalize what does it even mean to be safe and reliable and trustworthy. So the first aspect is to provide a language to designers, which goes beyond them just collecting data and providing it to the system. You need to be able to provide a language in which they can describe what is the desired behavior. And then the second part, which is now where we are really getting into machine learning territory, is to think about developing methods that can make ML systems compliant with these rules and specifications. Of course, they should optimize your empirical risk based on your training data, but that's not enough. You also want machine learning systems to be consistent with these specifications if the designer provides these kind of properties. And so over the last sort of 4 or 5 years, partly sort of driven by things like adversarial examples, there has been a lot of work in making sure that machine learning systems conform with these types of properties. Of course, this L infinity norm specification and adversarial example is a special case, but I'm talking about thinking about it broadly. And when you think about it broadly, I mean, there are three still technical pieces that you need to sort of work on. Rigorous testing of AI systems, where you really sort of stress test machine learning systems to see whether they are consistent with certain properties. Developing robust AI systems, which is to sort of find ways to sort of find mitigations and find sort of ways to sort of make the models robust. And finally, verifying AI. I mean, this is sort of still in its early sort of stages, where you can, one would hope at some point of time, we would be at a stage where, like software verification, you will be able to formally prove that your machine learning systems satisfy or are consistent with certain formal specifications. But I'll not be talking about these. So there's a lot of work that our team has done on these three sort of verticals, but I'll not be talking about that. I mean, so that could be a subject of another talk, and you should sort of contact me. I can give you sort of pointers to that. Or you can look at, I mean, the work that Alex has been doing, Vico Coulter has been doing. A lot of people have been working on this in this area. What I'll be sort of talking about actually are three sort of key case studies, which I have had the chance to be part of, which sort of really sort of talk about bring to the forefront the challenges that appear when machine learning systems actually interact with the real world. So the first sort of case study is around safety, and that's language model and toxicity. Now, of course, like as all of you know, in the last couple of years, one of the dominant sort of themes that has been in machine learning is the rise of these general purpose sort of language interfaces, driven partly by the work that has happened on the back of GPT-3. So we have pre-trained language models, and we have used them as a starting point for many, many tasks. The issue is that the language models can somehow implicitly encode biases that are present in the data, that in the large amount of data that is sort of given to them for training. And this is a safety problem because if these language models are used then for future applications or dialogue system or for completion of text, they can generate toxic language, and this can be a big impediment to deployment. So here, in this particular talk, I'll specifically focus on toxicity. And just to sort of formalize it, I mean, so what is toxic? I mean, for the purposes of this talk, we'll consider an utterance which is rude or disrespectful or unreasonable, and is likely to make someone leave a discussion. Now, it can sort of comprise of insults, identity attacks, obscene language, threats, but there are many other things that are not covered by it. And so this is the notion which we is based on work on prior work on language models, and it has also been the subject of this resource called Perspective API, which is used for online moderation. Now, there are a lot of caveats with this discussion. I mean, it does not capture a large set of language model harms. This notion is subjective, context dependent, and of course, there is ambiguity with this. So in the literature, of course, there has been a large number of mitigation methods that have been proposed to tackle this. So there are three sort of categories, broad categories. One is steering, which is an example would be this plug-and-play language models, where you train a toxicity discriminator on language model representation, and then use it to steer token generation away from sort of toxic language. So you are using your language model, but now you're using this additional discriminator to steer its predictions away from toxic generations. There is, of course, training data filtering, where you can sort of detect toxic language in the training data, and then score all your training sort of documents and filter out the toxic ones. Then there is test time filtering, which is like the real big hammer, where you take a model, say a fine-tune word toxicity classifier, and reject all language model output based on that prediction. So these are the three sort of categories: plug and play, steering, training time filtering, and test time filtering. And when you sort of look at the performance of these methods, based on sort of real toxicity prompts or non-toxic prompts, you will see that the standard language model has a high degree of toxicity, can produce toxic content. These plug and play sort of the steering based approach sort of is quite effective. It reduces it significantly, but still there is a lot of toxic language that could be generated by that. Training data filtering is even more sort of effective. And then test filter is actually quite good. But if you combine all of these things, then you get much better results. So what we wanted to study in the context of our recent sort of work, and this appeared in EMNLP earlier this year, on what is the actual behavior of a language model when you are trying to reduce toxicity in this way. So one takeaway from our analysis was that these automatic detoxification methods actually improve toxicity ratings, not just based on the automatic toxicity classifiers scores, but actually human scores. So if you plot the average human toxicity scores, where humans are asked about measuring the language, the toxicity of the samples that were generated, and if you look at the automatic evaluation scores, then you see there is a high degree of consistency and agreement. And furthermore, as you increase the intervention strength, that degree of consistency still remains. So these colors sort of show you the amount of intervention, or how much you are intervening in making sure that the final outputs of this whole system are sort of free from toxic phrases or language. And you see that both according to the automatic API, the perspective API, as well as from the human sort of toxicity assessments, they are getting better results. The second takeaway from this from our extensive analysis was that automatic evaluation becomes less reliable after you have done these mitigations. And there it just sort of tells you that there is some room for improvement in how you score these measurements. At the low levels of intervention strength, where there's a lot of toxic documents, you will see there's a high degree of agreement between the automatic perspective API and the human assessors. But as you increase the intervention strength, then you see that there could be sort of samples for which the automatic system would say that there's a high chance of a toxic sample, but the human assessor would say there is not. So it just shows you that a lot more work needs to be done in either sort of improving these automatic toxicity assessment predictors, or you need to rely on human evaluation at some point of time. The second sort of part of the analysis was what do you have to sort of pay for removing these sort of toxic language. So of course, one part is computational, where things like test time filtering are extremely computationally expensive. But because you are filtering even at the training time, and you are sort of in the steering-based methods, you are steering the model away from what it deems are the highest perplexity sort of generations, you would sort of suffer from your final sort of language modeling loss. So this sort of graph shows you that detoxification comes at a cost. And as you sort of increase your intervention strength of these mitigation strategies, you see that there is the loss that you incur for basically for removing this toxic sort of content is equivalent to training a language model with 1/3 of the parameters. So there's this delta that you had gained by having a very large model then sort of vanishes because you now spend that extra capacity in this mitigation approach. And there's this other sort of element where even these sort of assessments have social bias. And so you will have a lot of the material which will be correctly sort of classified as toxic, but there is essentially a notion that these classifiers learn to an explicit bias against certain identity terms. So if you have certain identity terms, then the model would say, well, this might be toxic language when it's actually not. So this is something that we really need to think about when we think about language models and how these are deployed in the wild. There is also sort of bias in the context of topics. So if you have a sort of this kind of a material where you have financial sort of statements, they will be considered sort of not toxic. But if you have sort of usage of certain words or certain identity groups, then even though the sentence is actually fine, it might be sort of considered toxic by these like overly sensitive classifiers. So in some sense, there is a lot of bias that's baked into the definition of toxicity itself. So there needs to be a lot more work to be done there, as was depicted by our earlier analysis, which showed that these the automatic assessment methodologies and the human assessors started to disagree when you started high intervention regimes. The same kind of bias sort of comes in dialects. So you would sort of say like general sort of language would be fine, but if you use certain types of slangs or certain types of lingo, that again it will be sort of considered that this might be toxic sort of content, and so this might be incorrectly sort of marked as toxic generations. Finally, what happens is when you increase the intervention sort of strength, the loss that you incur on the perplexity or on the language model task, that's not uniformly distributed across all the whole population. It disproportionately sort of affects the marginalized groups or the underrepresented groups in society, because there is less content on the internet available that is associated with these groups. And so if you use things like training time filtering or test time filtering, then it disproportionately sort of increases the loss in perplexity scores or the language model tasks corresponding to these groups. And that's true for both sort of gender as well as for sort of identity. So to conclude this part of the first case study, these notions of what do we want from a language model, things like toxicity, they are ill-defined, but that doesn't mean that we should stop working on them. It's just sort of this is a call to arms in terms of defining this more formally. We need to find better definitions. We need to sort of see how do we integrate these definitions into our models. And evaluation and mitigation at the moment is sort of useful, but it's still there needs to be a lot more work that needs to be done there. And of course, there are trade-offs between the actual language modeling sort of laws, as well as being consistent with these specifications, and that's fine. That is something that we will, as sort of designers of these systems, have to sort of make appropriate trade-offs. And also, like, when you think about toxicity mitigation, there are certain things that you are covering, but there's a large element of language work that is not covered. Microaggressions, stereotyping, these are sort of very difficult to capture, but it's still, there needs to be a lot more work that needs to be done in this area. So I'll sort of conclude the.
But just before moving on, there was super. Thank you. We've had a few questions about that, and maybe I'll try to summarize them to ask you to comment perhaps briefly on this issue of the challenge of how to define and monitor toxicity, which clearly is a subjective thing that different humans may feel differently about, and it's very difficult to automate. Can you speak to that briefly?
Yeah. So in this particular task, we used what was sort of what was considered in the community, in the literature, as a standard approach, which was this perspective API. And the analysis that was done is that if you consider that as a source of ground truth, first of all, it is not a ground truth, because we wanted to show that where does it fail, where does it work, and where does it fail. And so at certain levels, it does work. It covers a few aspects, and how it was trained is by sort of training or labeling toxic sort of content, and trying to learn a predictor which could sort of detect toxic content. Of course, this is subjective, and it's and the performance of that classifier is far from perfect, as the human assessment sort of show. So what is needed? I think, of course, a better system is needed for detecting toxic content. What we wanted to sort of highlight here is that, first, it has shortcomings, and secondly, at some point of time, you will have to rely on human sort of raters. And then there is a broader sort of topic which we did not touch upon, is subjectivity, right? And context dependent. For what might be toxic for one person might not be toxic for someone else. And so how do you get those notions of personalization and subjectivity? And nothing has been done in that context, right? So this was assuming sort of a universal sort of definition of toxicity, which everyone would agree on. How would you sort of apply that in the context of making language models safe? And that was the approach we were analyzing. I mean, we were not saying this is a solution. We were just saying, see, this is a path. It has a lot of challenges associated with it, even if you take this path, but there needs to be a lot more work that needs to be done in actually defining what the problem is.
Yeah, thank you.
So I'll conclude this sort of case study, and I'm happy to answer more questions, but by just listing all the people who are responsible for this sort of project, and the people who are marked by stars are the people who are the key members of the team who led this work. And if you have sort of questions, please sort of feel free to email them on this email address. And with that, I'll move to the second case study, which is AlphaFold. And I'll sort of talk about it in the context of reliability. So language models was in the context of safety, where there were certain specifications like toxicity, which are critical, should never happen. And how do you make a language model consistent with those specifications? Here we are talking about reliability, that this is a tool which is important, will be used by everyone. How do they trust it, that it has made the right predictions? So going back, to give you a sort of background, I lead the science team at DeepMind, and one of our key sort of central missions is to solve fundamental scientific problems with AI, leverage machine learning and AI techniques for key scientific challenges. And one such scientific challenge that we are very proud of having made a contribution in is predicting the 3D structure of a protein from its amino acid sequence. So a protein, like these are like basic building blocks. So if your body is like a machine, these are the Lego pieces that actually make that machine. I mean, they're not static, they move around as well, but they are essentially what make you and me, right? All of us. And so we don't even know what their structure is, let alone sort of thinking about tweaking with them. So we know like a small fraction of the proteins that make us. We know their structure before AlphaFold, and we've been able to expand that. So AlphaFold, the basic thing that it tries to do is, given a sequence of amino acids, a protein, so there are these 20 amino acids, and if you are given a sequence, you want to find what is the structure of that sequence. That's the basic protein structure prediction problem. There has been a lot of work in this area. So this particular assessment, so this community has been working on this for the last sort of 2 to 3 decades. There have been biannual assessments that happen, independent assessments that happen where everyone in the community sort of contributes their current results and their current sort of systems for assessors, and the assessors then sort of see what is the performance. And so the last year, it was the 14th assessment that was happening, and you can see the scores from I think CASP 7, which happened in 2006, to CASP 14, which happened last year. And you see like progress was. I mean, there were a lot of techniques were being sort of implemented, but progress was. There was some progress, but mostly the field was finding it difficult to move beyond this 40 GDT mark, which is sort of a metric for evaluating the accuracy of protein structure prediction. So DeepMind sort of entered the first time in this assessment in CASP 13, which was in 2018, and we sort of went to 60 GDT, but we really wanted to actually make a big difference in sort of solving this and in solving this whole problem so that people can use it. And in CASP 14, we made a remarkable sort of breakthrough, and it was AlphaFold 2 was the highest sort of accuracy method, and it was considered by many people as really solving a variant of the structure prediction problem. So how does it work? The short version is that there is a 62-page supplementary sort of material appendix that comes with the Nature paper. So I'm not going to be talking about all the details of what went into the method, but like it is a deep learning architecture. It takes the input sequence, sort of goes through a genetic database search, finds multiple sequence alignments, residue pairs, and other sort of template matches. These are then fed into an informer architecture, and finally it gives you a structure prediction. But this structure prediction is this prediction of a structure is not enough, because now you have biologists who might be using this for understanding a particular biological mechanism, or might be thinking about how do you design a drug that binds to this particular protein, or finding sort of an antibody that binds to this particular protein or whatever. So they need to not only sort of look at this prediction, but also think about what is the reliability associated with this prediction. So understanding uncertainty and reliability are key elements, because the AlphaFold will give out these predictions, and these are extremely important proteins. And a lot of biologists, some have sort of dedicated their whole lives studying these proteins, and you don't want to mess around with those predictions. You really want to understand and give any guidance that you can on how accurate those predictions could be. And one of the fundamental breakthroughs that I personally believe that AlphaFold 2 was able to achieve is this understanding of uncertainty using deep networks. So what we did is basically, now just to go back, so we had this informer, evoformer sort of layer, and this structure module, which basically gave the final prediction. And of course, there was this recycling step, which fed the structure back, and so on. And this architecture, there were a lot of interesting things about this architecture, which I'm not going to go into the sort of a lot of details on. But finally, what we did is we looked at the underlying representations and used them to make predictions about uncertainty, and two types of uncertainties. about whether the model has got the correct prediction. So the first kind of uncertainty is called a local sort of uncertainty. It behaves like a local confidence measure. It's called PLDTT. It sort of thinks roughly at a high level. It sort of measures the percentage of correctly predicted interatomic sort of distances. And so this is computed at a per sort of residue level. So for a per sort of amino acid, you can sort of think about how accurately has that amino acid or that sort of a residue being accurately sort of isolated. And then, and this is sort of how an uncertainty measure sort of looks. So this is the protein. So on the x-axis, in the graph in the bottom right, you will see the number of residues. So for a particular protein, like in this case, it has, I think, 75 amino acids. And you can see the PLDT score. If the PLDT score is really high, you know that for those residues, you have high confidence in sort of trusting the structure. Where the score is low, like in orange or yellow, there you think, well, I'm uncertain about whether those things have been correctly isolated. So this is about the isolated PLDT score. And it can be used for a number of purposes. It can be used for identifying domains and disordered regions. So proteins, they are like these Lego blocks. They can be static, but they can be sort of disordered. And so this, if you see that AlphaFold is quite uncertain, it might be because this is a disordered region and it does not have any structure. And it can also be sort of used as assessing confidence within a domain. So these proteins can be divided into certain domains which have quite static structure. And so you can think about what is the structure of that particular sort of domain. However, it has these big pitfalls, this particular measure. It does not imply the confidence in relative positions of the domains, because in a protein, there are these domains and there is some degree of sort of movement between the domains. So these scores are local. They don't sort of tell you whether the domains have been correctly sort of configured in the final sort of prediction. And so PLDT does not sort of assess that. For assessing that kind of uncertainty, we had this predicted aligned error, which where the idea is that what is the position error at sort of amino acid X, residue X, if the predicted and the true structures were aligned on residue Y. So it's sort of a relative sort of error. So you think about this this matrix, this co-occurrence matrix, where you look at what is the expected sort of position error. And so you will see that, of course, for things which are extremely close by, you have sort of low expected error. And as things sort of move away, sometimes if you sort of cross in a different domain, as this protein shows. So this protein has these two domains, and they're connected by this linker. And so there is less confidence. There's sort of high error in any sort of residues that run across this linker. So the 272, 163 has a sort of high low error, and 272, 429, which is across two domains, they will have sort of a high estimated sort of error. So they can sort of be used for confidence in like predicting domain packing, whether the domains actually are correctly isolated or not. So what was very interesting about AlphaFold's release is that when AlphaFold was released, it was released as a protein structure prediction method, right? You give in a sequence, you will get its structure. That was what it was trained on. But then when we got the feedback, and now a lot of research these days happens on Twitter, because you get you get a live stream of responses and feedback on your results. So when people sort of tried the open source code, they saw that AlphaFold's uncertainty predictor was actually better than was really sort of remarkable in detecting disorder, like which parts of the protein are disordered or do not have a specific structure in isolation. And so that, I think, is a true test of an uncertainty estimate, where if the uncertainty tells you that uncertainty estimate tells you that, well, I don't have a confidence in this prediction, and in fact there is no true answer there, that's sort of saying a lot that the model has got something right. So we were very happy when we saw this sort of result. Now, of course, AlphaFold has been open source. We also created structures for many proteins and shared them with in this database in partnership with the European Molecular Biology Lab. There's of course AlphaFold Colab, and also we have open sourced the code. It has had a lot of impact, and this just shows you the power of machine learning and AI, and the responsibility on all of us as machine learning scientists in leveraging this tool and leveraging this technique properly, and really utilizing it for the benefit of the scientific community and society today, because this is really a very powerful technology. So I'll just mention this database that for the first time now biologists have access to this kind of a database, and we had to sort of do this whole invent this whole sort of technique of how do you present uncertainty at this large scale, because biologists were not used to looking at structures in this way. So this was sort of a new thing. So there's a large team that deserves the credit for this piece of work. Adrian, how much time do I have?
Sorry, Pushmeet. We've got 10 minutes, including questions. But so it's up to you. I think we can have not many questions if you want to talk about your next topic, or what do you think?
Yeah, so I'll maybe spend a couple of minutes on the next topic, and I'll just rush through the second topic, and then I wanted to leave time for questions. So Perfect. The last thing that I wanted to talk about was a paper that actually came out last week, which is AI for Maths, which touches upon another element of what I was talking about earlier. So safety, reliability, and the third thing was trustworthiness. And there in trustworthy AI, one of the key central elements in it is interpretability. And I just wanted to sort of highlight this work that came out last week, where we showed how machine learning scientists and a machine learning system working in collaboration with some of the top mathematicians in the world, and then they using it to make a number of key surprising discoveries, which are really sort of significant for mathematics, not as a machine learning sort of result, but as a maths sort of result. So there were sort of three topics on topology, abstract algebra, and sort of number theory, and we were sort of collaborating with sort of some of the key sort of mathematicians, the top mathematicians in the world on this topic. The actual math results have been written as separate papers, the things that were discovered by this sort of system, and working in collaboration with the mathematicians. And just to sort of mention that this is one of the, like, the image on the left is Ramanujan, and it's basically one of this idea that intuition has driven a lot of research and advance in mathematics, and machine learning systems by analyzing the patterns and data sort of have the potential to really add a lot to the mathematics research that is happening. I'll not go into the details, but just sort of mention that we looked at two topics, representation theory and knot theory. The general idea was that there were these two types of invariants, like in knot theory, geometric invariants and algebraic invariants, and there was no connection known between these invariants. And somehow by learning this connection and then sort of understanding what that connection could be and how that connection is derived, we were able to sort of come up with this. This is the conjecture, which somehow unifies these two fields together. And that is the real significance of it. And the interaction between the machine learning system and the mathematicians came in the form of a lot of analysis and sort of attribution techniques, which showed mathematicians how the system might be making and predicting one quantity from the other. And then with that, just I'll recap. I've considered sort of safety in the context of language models, reliability in the context of AlphaFold, and interpretability in the context of AI for maths. And with that, I'll just stop by just highlighting that in terms of future work, I think there is this social challenge in sort of taking machine learning beyond test sets. I think this is something that as we see machine learning getting deployed in the real world, we have to move beyond test sets and really think about what is a more unified, holistic evaluation of the system implies, and thinking about specifications and specification-driven testing of AI systems. And then, of course, on the technical side, the challenges in our formalizing these specifications. Sometimes these are hard to formalize, like we discussed Toxicity as an example, and then scaling these techniques to larger and more complex models. So with that, sort of I'll conclude. And this is sort of not just my work. This is a lot of teams at DeepMind, the AI for Science team, Robust and Verified AI team, and Applied Research deserve the credit for this work. So with that, thank you.